This video is going to deal with the concept of internal resistance. It's something that we encounter in all real-life batteries or cells. When you started studying circuit electricity, you probably would have ignored this particular concept. But as we go on in our studies, we need to recognize that internal resistance is a feature of all cells, and we need to be able to take that into account. The way that internal resistance is illustrated in a circuit is by showing the cell, as we would normally, and then putting a small resistor labeled with a small r next to it, and then a dotted line surrounding the two to indicate that that small resistor forms part of the cell. If we had to define internal resistance, we might define it as the resistance that's offered to the flow of ions inside a battery. So up until now we would have ignored that particular resistance, but from now on we will consider it as part of the feature of the particular electric circuit that we're looking at. Before we get into the details, let's just remind ourselves of the difference between EMF and potential difference. Firstly, EMF. EMF stands for the electromotive force, and that refers to the voltage in a circuit in which the charge is gaining energy. And as charges move through the cells, they gain energy, and so a cell or battery would be an example of where electromotive force needs to be taken into consideration. In contrast, if we just use the word potential difference, we then are referring to a voltage in which charges lose energy. And a resistor is a good example of that. As charges move through a resistor, they lose energy by transferring that electrical energy into some other kind of energy. So if we look at a very simple circuit that has a cell and a resistor in it, and we look at the voltage V1 over the cell and V2 over the resistor, then V1 would give us the EMF, or would define the EMF, and V2 would be the potential difference. And in a very simple circuit, if we're ignoring internal resistance, then V1 would equal V2, but we'll talk a little bit more in detail about that now. So EMF, electromotive force, is a voltage in which charges gain energy, and potential difference relates to a voltage in which charges lose energy. All right, let's just quickly consider a normal real-life cell. Here's a diagram of a cell, and if you haven't already, you certainly will study some of the redox chemistry that allows you to understand how these cells work. But just remember that the cap on the top end of the diagram indicates the positive side of the battery, and the flat end on the other side indicates the negative. And if we had to connect those up, piece of wire, then electron flow would be from negative round to positive. But that area inside the battery that contains the particular chemicals that cause the redox reaction, within that area we have a flow of ions. And as those ions move and electrons move through, there is some resistance to their movement, and that's the internal resistance of a cell that we are now dealing with. So if we take an ordinary circuit, we've got a cell with a small little resistor indicating the internal resistance, and we can put a little dotted line around that to indicate that that refers to the battery. We have a switch, an open switch at the moment, a resistor in series, and an ammeter in series. We put a voltmeter over the battery, and let's start by considering this situation with the switch being open. While the switch is open, obviously no current flows through the circuit, and because no current is flowing, there is no opportunity for energy to be lost in the battery. And so the voltmeter over that battery would read the EMF, the full charge that would be given, the full amount of energy given to a coulomb of charge as it passes through the battery. Let's just imagine for our sake that the EMF of this particular battery is 12 volts, and the voltmeter then over that battery would read 12 volts. If we then close the switch, the first thing we notice is that there's a drop of the voltmeter. It was at 12 volt, it's now reading 10.5 volts. And so our first observation is that there's a voltage drop registered over the battery. We refer to that voltage drop as the lost volts, and the reason for those lost volts is that energy is required to overcome the internal resistance. And so as charges move through the battery, some energy is lost simply overcoming internal resistance. And so the voltmeter reading now, which is showing only 10.5 volts, is reading the external voltage of the circuit. It's the voltage that's left over once the charges have moved through the battery to be used in the external circuit. And we often refer to that as V external, the little subscript there, EXT. Let's get rid of that now and consider some of the formulas that you'll be needing to use in this section. This is the formula that appears in your data sheet. E for EMF is equal to big I, that's the total current in the circuit, times by big R, which is the resistance of the external circuit, plus small r, which refers to the internal resistance. Let me explain where that formula comes from. So far in our discussion, I think you can see that the total EMF is made up of two parts. It's the voltage that's available in the external circuit, plus the voltage that's being lost internally within the battery, and so we refer to that as V external plus V internal. And the V internal gives us our lost volts. Now, applying Ohm's law, V is equal to IR, so the external voltage is equal to the current, the external current, big I, and the external resistance, capital R. The internal voltage, or the lost volts, again is the same big I, because the current that flows through the battery is the same current that flows through the rest of the circuit, and then times by the internal resistance of the battery. And if we simplify that, we get the equation that we see in our data sheets. Alright, applied to our little example here, we said the EMF for the battery was 12 volts, and when we closed the switch, the voltmeter read a V external value of 10.5, and if we solve then for V internal, we can see that 1.5 volts is lost in the battery, and that then gives us the amount of lost volts. Alright, if we just add in some numbers, and let me just show you quickly how some calculations might work. Let's imagine that the current in the circuit is being read as 5 amps by the ammeter, and that the external resistor there has a value of 2.1 ohms. So if we apply our formula from our data sheet, the EMF we said was 12, the current I is 5, and the external resistance of the circuit is 2.1, and if we then solve that simple equation, we can see that the internal resistance of the battery would be 0.3 ohms. Let's now look at a question from a past paper. Here we have a battery with an EMF of 12 volts, and as indicated in the diagram, the EMF is 12 volts, and the internal resistance, little r, is given as 1.5 ohms. You'll notice also that we've got two 60 ohm resistors in parallel, and then we have another 25 ohm resistor in series with those two that are in parallel. Alright, let's have a look at the first question. It asks us to calculate the equivalent resistance of the parallel combination. Now, this is something we would have done before. Remember, the formula is 1 over R parallel, it's 1 over R1 plus 1 over R2, and in this case that's 1 over 60 plus 1 over 60, which gives us 2 over 60, and then don't forget to work out R parallel by itself. We need to invert that, and so we invert the 2 over 60 to get 60 over 2, and that gives us the parallel combination of resistors as 30 ohms. Another way to do that would have been just to remember that where you have two equivalent resistors in parallel, their combined resistance is just half the value of one of the resistors. Alright, the second question asks us to calculate the total current in the circuit, and now we're pulling out our formula from the data sheet. EMF is I big R plus little r. In this case the EMF is given as 12. Big I, the current, is what we're looking for. The total resistance of the external circuit is given as 30, that's the combined parallel resistance, and then adding in the 25 ohm because that's in series, and then little r is given as 1.5. If we then solve for I, we get a current of 0.21 amperes.